Fantastic. I'm not going to read out your Professor Ger Finlay's biography, but you're all very familiar with his profile. So, Ger, maybe you can introduce yourself, if that's okay.
Sure, Raymond, thank you very much. And it's great to not see everyone again, I suppose. It's not right to say I see you all because I can't see anyone other than my slides, but it's good to be back at ISCE. I think the first meeting I attended was in 2004 in Florida, and I've been a fairly regular attender since. So Raymond has invited me along today to talk a little bit about an aspect of ECG processing and feature engineering for machine learning. But before I do that, I want to welcome everyone on your side to where I am. So I'm actually joining you today. I'm from University of Ulster in Belfast, obviously, as most of you know, but I'm joining you today from where I come from, my home, where I grew up, which is a small village called Gordaclair. It has a population of 66, not 66,000, 66, okay? It's about 60 miles west of Belfast. You can see here on the map on the left where we are in the United Kingdom and Ireland. And then on the next map over, you can see where I am relative to Belfast, about 60 miles west of Belfast and about 10 miles from the border with the Irish Republic. I've got a picture here of some of the scenery around here. It's a fairly rural area, agricultural area. On the very right, I have a picture here from 1943, and that's where the American soldiers were based here, just in the small village where I live. They set up here and trained for deployment in Europe before they went to France, I believe these guys actually went to. This is a picture that has been digitally restored to colour, which was taken just across the way here from me. So thank you very much. So the brief that I've been given by Raymond was to come along and deliver this tutorial on how features are considered in ECG interpretation. In the main, my focus will be on trying to demystify how measurements, typically used in diagnostic interpretation, have classically been harvested from the ECG. And I also want to contrast that to the traditional approach to this task, I want to contrast that traditional approach to how things now work in the more AI-driven and deep learning approaches. And I have to stress, this is very much a very basic tutorial, and it's certainly not for those who are very well versed and have done 40 years of ECG algorithm development. This is for people at the very much the earlier stages of their career in that. So I want to just have a look at this slide to provide some context. And I want us to think about the vehicles down the left-hand side. Now, most of us as human observers obviously look at these vehicles and are very easily able to say which of the three categories in the middle of the slide that they fall into. So the top one's obviously a car. The next one down is obviously a truck. The third vehicle down is obviously a car. We have a motorcycle, and we have another truck. And that's pretty obvious to us. But if I asked you to think about what actually is important in making that decision, it's more of a challenge. What do you actually do when you look at these vehicles to decide if they're a car, a truck, or a bike? And if we said, well, let's actually write a computer program to do this. Let's write an algorithm that will look at these vehicles, take something from the vehicles, and decide which of the categories. It's a much more challenging problem then, because then we start thinking, well, what are the measurements we can take from these vehicles? We can observe that the vehicles have a certain number of wheels, they have a certain engine capacity, perhaps, they've got a certain colour, they've got a certain length, they've got a certain weight, all sorts of things we can observe from the vehicles. But are all those valuable in making that decision? Well, we don't really know. There are also things that we can look at secondary to the actual vehicle itself, things about the owner, the environment that it operates in, maybe tells us what kind of vehicle it is also. And then there are things that we can derive from the vehicles. We can measure the performance, the number of miles per gallon, how long it takes for them to stop when they're doing 60 miles per hour on the highway, and those things may all help us decide what kind of vehicles they are. But that's very, very different from us as human observers looking at them and saying, okay, car, truck, car, motorcycle, and truck. That's pretty easy. And that's really the challenge in ECG interpretation in a nutshell. So I'm moving on to this slide where I have a number of boxes, and I'm going to talk through each one from the left. For most of us nowadays working on ECG analysis, signal processing, AI, our ECGs arrive to us in a set of numbers, basically. That's ground zero of our ECGs. They're sample digitally stored, and here we have 8 channels of the independent information that make up the 12-lead ECG. We've got 1,000 samples per second in this example, and on the top left-hand side, we have something that looks like an Excel spreadsheet with the numbers for each lead, the first 30 samples, roughly, first 30 milliseconds. And in order for a human observer to make a diagnosis, based on those recorded samples, we ultimately want to draw what's on the top right here, this picture, which looks like a 12-lead ECG. In order to do that, there's some modest processing involved. We calculate the extra leads over and above the 8 channels, the extra limb leads, and maybe do a little bit of filtering and processing and arrangement of the signals to allow us to draw the 12-lead ECG. Now, a little bit like the example where we had the vehicles and we had to decide what category they're in, a human observer looks at the ECG and probably does apply some sort of rules. Here we have the rules on the bottom right-hand side for the current definition of ST segment elevation MI. And the human observer, along with some knowledge, intuition, experience, training, a lot of things we can't really quantify as well, will apply those rules to the signal and make a diagnosis. Now, whenever we actually start to think about what the human observer actually does, what do they do? What do they look at the measurements? Do they analyze the waveforms? Which part of the waveforms do they look at first? The challenge in replicating this is much more difficult. And that's what human or computer interpretation of the ECG has typically involved. Typically involved somehow taking those rules, trying to apply them to the signal that somebody would have visualized, but obviously we don't see the signal, or the computer doesn't actually look at the signal. Typically it looks at the raw data. But the process that has typically been used over the years, or from the beginning, is to take the raw ECG signal, perhaps do some processing, pre-processing, filtering, etc., and then from that raw ECG, try and establish the features of the ECG, intervals, amplitudes, areas, some related features, a little bit like the vehicles that we looked at, the sex of the owner of the ECG, the age of the owner of the ECG, and perhaps some derived features, perhaps some areas, etc., eigenvalues that can be derived from the ECG, and then somehow apply those rules to the ECG. Now, at the very end of this presentation, I'm going to show in contrast how that has changed with modern approaches to deep learning. But before doing that, I want to actually spend the majority of my time thinking about what's happening inside this top right-hand box here, this feature harvesting stage of the ECG. And this is where I have to stress again that this presentation is really not for those well-versed in this, but it is something that some of us have commented on and observed, that over the recent years, ECG meetings have less of this kind of activity and typically have more of the deep learning approach to life, where these things are not so much discussed or talked about. So I want to refer to Paul Cligfield's article here from 2007, the recommendations paper, where in that article, Paul and his colleagues looked at the various stages or made reference to the various stages that typically happen in computerized interpretation of ECG: pre-processing and filtering, beat detection and classification, segmentation of diagnostic waveforms, waveform picturization, and diagnostic classification. That's a very generic outlook in life. For a more specific synopsis of what medical device manufacturers, the big algorithms commercially available, are doing, I refer you here to another paper of Paul's, reference number 2 on my slide, which gives a very specific paragraph on each one of those algorithms as part of the study that was done. But the remainder of my presentation, I'm going to focus on these 5 points, because, again, that's not something that we typically find at ECG meetings now, coverage of that material. And indeed, whenever we're teaching this to our biomedical engineering students, certainly in my institution, I find we're looking very, very far back in the literature, in the textbooks, etc., to actually to cover that material. So the first stage of this process that I want to cover is signal filtering. And this obviously seems quite magical. We're removing parts of the signal we don't want. For those who are not familiar with digital signal processing, I want to give 2 brief perspectives on what we're actually doing at this stage, at the very first stage of the computer interpretation and extraction of those measurements. One perspective is that, in theory, every signal in life, an ECG being one example, is made up of a combination of an infinite number of sine waves. And what we're basically doing at this stage is we're removing the sine waves that represent the noise that we don't want in the signal. And that's what I'm showing in my diagram here. On the right-hand side, we have a bunch of sine waves. They go together in a certain way. They make up the ECG. We take out the ones that represent the 60 hertz mains noise and take out those that represent the low-frequency noise and the high-frequency noise. We're filtering our ECG. And from a very practical perspective, again, when we meet our biomedical engineering students who are perhaps less scientific, less computer oriented, less mathematical, it's sometimes something we take for granted that they understand. But basically, practically what happens here is we basically move through our signal, the samples of our signal, and we perform some operation by combining those samples using a linear combination of the samples, previous outputs, and that gives us our filtered signal. Now, moving on, in the method that I want to discuss here, following on from Paul's 5 steps, I want to have a look at what we do to try and find where the basic beats are in the signal. And the first thing that we do here is we take our 12-lead ECG and we transform that to a VCG signal. And what we're doing there is we're going from the 8 dimensions effectively of the ECG and reducing that dimensionality to 3 dimensions, the X, Y, and Z leads of the VCG. At this stage, we have no intention of using the VCG signal in any kind of diagnostic outcome. We're doing this basically because this reduces the variability in the various ECG waveforms that we see. And the next stage, we take that VCG signal and we compute this spatial velocity signal. So when we calculate the spatial velocity, what we do is we take the difference between the samples in those 3 VCG channels, take the square of each one, add them together, take the square root of that, and we get a signal that looks something like this. This is 1 cycle here represented. Now, by doing that, what we've done is, again, we've removed more of the variability that we see in different kinds of waveforms in ECG and different leads, and we get a very standard-looking ECG, or a very standard-looking waveform across many different ECG morphologies. And what we can do is, if we look, I'm citing a reference of Peter McFarlane's here, going back quite some time. What we do is we move through this signal. Again, I'm still focusing on the top waveform here, and when we reach a point as we move through this of 50% of the maximum of that signal, we know we've probably found a QRS complex. We move backwards until we find a critical value of 3 millivolts per second, and at that point, we establish that we've roughly found where the QRS onset is for all of these leads that were in our 12-lead ECG. We move in the other direction, we do the same thing again, we find 3 millivolts per second point, and we know that that's roughly the end of the QRS. Now, in the slide here, you can see below that I've got 3 complexes with the spatial velocity signal, and beneath that I've shown lead 2 of the same ECG, and you can see that roughly we found quite well where the QRS onset and offset is. After that, we build a table of all of the onsets and offsets. I've done it here in sample number, and we get a bunch of those, and we can work through those later as our rough starting point for a QRS onset and offset. Now, at that point, whilst we did filter the signal, often some baseline wander still does exist. So what I'm showing here is after we found the QRS onset in this signal, we've actually found a point roughly in the signal that should be at 0 volts. So we went along here, and these red circles, I hope you can see those on this top waveform, should be roughly at 0 volts, but you can see they're not. That baseline wander is there. In the second graph here, what we've done is we've fitted a curve to those points, and I've intentionally chosen this segment of the ECG because it highlights a problem with this approach, although the approach is quite robust. What we've done here is we've fitted a yellow curve to those points, and in the end, we subtract off that curve from all of the ECG samples, and you can see in the bottom that gives us a fairly stable ECG using a cubic spline fitting curve here, by the way. Now, again, I've used this example for a specific reason. You can see at one point, about 8 beats along there, things go a little bit wrong, and the signal hasn't been corrected properly. And often when this is done, the people ignore some of the beats in the QRS complexes where they just simply deviated too far from the baseline in the first place, and move forward from that. So once we've baseline corrected the signal, we're in a good position to actually make an average complex that we can actually get those measurements from, that we can use to inform our diagnostic process. When we do that, we typically, before making the average complex, we look through all of our QRS complexes, all of our beats. I'm only looking at the QRS here. Typically, in the broad scheme of things, you look at all the wave components, but for the sake of speed of working through this, I'm only focusing on the QRS. Again, still thinking with that example of the ST segment elevation criteria, which we'll look at next. So what we do here is at this stage is we look through all of our complexes, and we try and establish if any fall too far outside of the standard looking complex that we have. We typically screen during that process for premature beats with excessive noise, and beats that perhaps fall too far from that baseline that we saw in the previous baseline correction. After that, we build our average complexes, 10 or 15 beats, take a median or an average of those. And at that stage then, on the right-hand side here, you can see where I've drawn the 12 average complexes for the ECG. Given that we found the QRS complexes using the spatial velocity signal, what we need to do now is make some adjustments potentially for each individual lead where the QRS complex may end and may start earlier or later than that global complex that we found. Once we've done that, we're in a position to actually apply our rules to that data. So we've got these measurements. Typically in real life, we've got hundreds of these measurements from each lead for all different wave components. And then we can actually apply. In this case, we've got our measurements on the left-hand side. I've noted the STEMI criteria on the top, and then we write code that logically works through that criteria and uses if-then statements to actually make a decision. So that was a very, very fast run through what you typically would do in the steps to get to have measurements that you would look at. Again, I'm thinking about the process where a human observer looks at an ECG, can probably harvest those measurements themselves and apply the rules and not really think about it, especially a very experienced electrocardiographer. But in a computer program, you have to do all of these steps to find those measurements to apply the rules. And that is quite processing intense. There's quite a lot of work involved. And I know many of us in the room, or many of you in the room, have significant experience working in medical device industry, for example, for many years. But as we see potential medical device engineers coming along through our doors, biomedical engineering students, undergraduate students, they have quite a lot to learn to get up to speed on this. Now, I'm saying that to make the contrast with what potentially is the case in the modern deep learning approaches. Before I do that, I want to just focus on, I've got three banks here, if you like, of citations. I've got the very top, got a number of articles published in the late 60s or early 60s and 70s into 1980. And those articles, if you want to find out, or if I was standing at the front of my classroom talking to my biomedical engineering students, it's those articles I would point them to learn about what I just talked about, that very, very brief summary that I gave of those steps. In the middle period, if you like, we'll call this the shallow learning period in the mid to late 90s and into the early 2000s. And indeed, there's a paper published there by Joel Zhu in the pink box here. People in the research community were looking at how we would still do those steps, harvest those measurements, QT duration, QRS duration, J-point amplitude, etc., and perhaps feed those into a conventional neural network, a shallow learning neural network, one or two hidden layers, try and replicate the actual decision-making stage rather than having rules, but still have the pre-processing stages of actually harvesting the measurements. In very sharp contrast to that, the articles that we're seeing, some of the more popular ones here with high citations I've listed in the green box at the bottom, what these approaches typically do as an extreme, I've depicted in the top left. Basically, in these deep learning approaches, in some of them, there's no pre-processing, no even filtering of the data. We just dump in the raw samples into the convolution neural network, for example. There's no thought into where the QRS falls, what the QRS duration is for any particular complex, any particular lead. Raw samples in chunks of 256, 1000 into a neural network, and very nice results come out of the other end. And it does work quite well. In some cases, though, we see a hybrid. We see guys who are taking the measured features that we talked about extracting and putting those along with the actual samples into a convolution neural network type architecture and getting favorable results as well. And indeed, the Computers in Cardiology Challenge, I think from last year, the winning team did something like that where they had a hybrid of both approaches. And that almost brings to an end my presentation. Again, I'm not approaching this as an expert in ECG signal processing, but something we do reasonably well is we try to bring our biomedical engineering students quite far along the road of understanding how ECG processing works at our university. It's something that we have quite broad in the syllabus, giving our expertise. And I find myself, like I say, talking to these students and pointing them to literature that existed in the 1970s. And I have an example of a book of Peter's, which is always a line around. It was actually recommended to me by a past student, and I bought this copy from a library, secondhand. But I suppose the point I want to make, the philosophical point is, and the question for discussion is, if we were at SK, we could have a beer later and discuss this, is does deep learning offer the ability to better model the elusive human process. So I think there are limitations in trying to extract those measurements and trying to do, again, if we think back to the trucks and the cars, if we ask you to write down the features that would allow someone to decide, it's much harder than just looking at them and making the decision. That becomes a much more complicated problem. So modeling that human process has been challenging. The same applies for ECGs and the conventional approach to tackling ECG interpretation. But do deep learning approaches get around that by just dumping in the data and letting the algorithm worry about it? In saying that, if we do find ourselves much more aligned with that approach, and we can see evidence of that, like I've said at the meetings now, many more articles on deep learning from groups that we never saw doing ECG research before, is there a potential to lose domain knowledge? Because when we look back to the work that I've cited in some of these articles from the 60s and 70s, these guys were doing a lot of work of putting something back into the community. They had to learn a lot about ECGs, complex durations, waveforms, understanding the signals, and that indeed was a form of knowledge engineering, and inevitably informed the ECG community, even though it was really focused on ECG algorithm development. And that's really all I have to say. I have to give one last perspective just on when I was looking at Peter's book and trying to find a reference to it. I found this book review from 1975. And what does this person say about Peter's book? Well, they say, this book should be read by every physician in charge of a large cardiac department who is faced with the problem of an ever-increasing load of cardiography. It will not offer him any instant solutions, but it will prepare him for the future trends. Many of them are likely to feel, however, that £2.20 is a lot, even these days, to pay for a 115-page paperback with no half-tone illustrations. And that's the end of my presentation. Thank you.
That was an excellent talk, Stuart. Really, really insightful. I really did enjoy it. So you'll see some questions. There is one question already, Stuart, in the chat. What method have you used to reduce the dimension of your beats? Was it PCA? Okay, so in the example that I used, just for the sake of working through an example, we calculated the VCG from the 12 lead, 8 channels of the 12 lead, using the Golden Ring matrix. And then we calculated the spatial velocity signal to reduce to one single one-dimensional waveform, which gives a very good characteristic shape regardless of the morphology of the underlying beats, and is very reproducible. And indeed, I believe that whilst the method is dating back to 1970s, people do use that still. It has been reported recently. Great, thanks, Stuart. Any other questions? Johan said he likes the citation. I assume that's Peter's book. £2.20 does seem like a lot, Peter. Raymond, I can see a question here. How is deep learning performance on unprocessed ECG affected by noise like baseline drift? Wouldn't it be better to do some pre-processing even for deep learning? Jeffrey, thanks for the question. I'm far from being a deep learning expert. My understanding, and there's probably people much better informed in the room, and maybe even Raymond, is that the early layers, typically of the network, are effectively the filters. They basically learn the filter coefficients in those early layers. So you will find people in the literature who have pre-processed the signal using the standard filters or more aggressive filters and baseline correction, etc. But many people are, and indeed, not only are people dumping in raw samples, people have looked at putting in just the image of the ECG as well, in an image processing type problem. Yeah, excellent question. I would say that from memory, one of our PhD researchers is doing some preliminary work on that. And I think from memory, what they're finding is that you're better training deep learning algorithms on good data, good ECG data, clean data. We had thought that if you expose it to noisy ECGs as well as clean ECGs, it would generalize better and have more understanding of the edge cases. But actually, I don't think that turned out to be the case. So having good archetypical ECGs in the training is very important. But, you know, it remains to be seen. There still needs to be more experiments. That's a good question. Raymond, there's a question here from JP, which I think is very important, actually. Very important point. JP's question is there any existing machine learning libraries you would recommend for ECG feature extraction? I think an issue, JP, is that
the basic things that were talked about just now for getting QRS complexes, etc. That's easy if you work for some of the big device companies and you can throw your ECGs in there. For a group like us, trying to do some of the basic signal processing on raw ECGs, it's quite difficult, and I'm sure many other groups are the same. And the understanding required to do that is not trivial. It is quite difficult to do that to a level that's acceptable, even for research purposes. Nowhere near medical device grade purposes, but I think it's easy to forget that getting a vector of measurements to do some machine learning work is trivial. It's far, far from it, and not everyone has access to the tools to do that, or the knowledge to develop those tools.
Yeah, so there's another question from Salah. Do you think a larger sample size data set is needed for unprocessed ECGs fed into a deep learning model? So I think what you're asking, Salah, is if your data set is noisy, do you need a larger sample? Sure.
I'm going to have to defer that to a deep learning expert. I think.
I mean, the deep learning from my understanding, Salah, in deep learning anyway, there is a form of filtering, because as you go through the layers, it does throw away noise. That's what certainly the convolutional aspect and the pooling aspect does. It goes through dimensionality reduction, essentially, is my understanding. So it does have its own kind of filtering built in. Okay, so is there any other questions? I just want to make sure I don't miss any in the chat. Okay, so there is a break now. There's no other questions. So we do have a break for a few minutes, and we will return. Supposed to be 10 minutes, but now we have 7 minutes. So we will return after that and enjoy the break. And hopefully you'll be hearing from Joel Zhu after the break. Thank you, everybody.